LC oscillations. When a capacitor which is initially charged is connected to an inductor, the charge on the capacitor and the current in the circuit exhibit the phenomenon of the electrical oscillations similar to oscillations in mechanical system. Let us consider Qm as the charge in the capacitor at t equals to 0. Then according to Kirchhoff's loop rule, Q by C minus L di by dt equals to 0. I equals minus dq by dt in the present case as Q decreases, I increases. Therefore, d2q by dt2 plus q by Lc equals to 0. Note that this equation has the form d2x by dt2 plus omega naught square x equals to 0, which is the equation for a simple harmonic oscillator. The charge therefore oscillates with the natural frequency omega naught equals 1 by root over Lc and varies sinusoidally with time as Qm cos omega naught t plus phi. Since Q equals Qm at t equals to 0, we have cos phi equals 1 or phi equals 0. Now as phi equals 0, the equation reduces to Qm cos omega naught t. On differentiating it, we get the current I equals Qm omega naught into sin omega naught t, which can be written as Im sin omega naught t, where Im equals Qm omega naught is the amplitude of the current. Let us now try to visualize how this oscillation takes place in the circuit. The figure shows a capacitor with initial charge Qm connected to an ideal inductor. The electrical energy stored in the charged capacitor is half Qm square by C. Since there is no current in the circuit, energy in the inductor is 0. Thus, the total energy of LC circuit is half Qm square by C. At t equals to 0, the switch is closed and the capacitor starts to discharge. As the current increases, it sets up a magnetic field in the inductor and thereby some energy gets stored in the inductor in the form of magnetic energy. As the current reaches its maximum value Im at t equal to t by 4 as shown in the figure, all the energy is stored in the magnetic field. You can easily check that the maximum electrical energy equals the maximum magnetic energy. The capacitor now has no charge and hence no energy. The current now starts charging the capacitor, as shown in the figure. This process continues till the capacitor is fully charged, that is, at t equals t by 2. But note that it is charged with a polarity opposite to its initial state. The whole process just described will now repeat itself till the system reverts to its original state. Thus, the energy in the system oscillates between the capacitor and the inductor. The LC oscillation is similar to the mechanical oscillation of a block attached to a spring. As noted earlier, for a block of a mass m oscillating with frequency omega naught, the equation is as shown. Here, omega naught is equal to root over k by m and k is the spring constant. So, x corresponds to q. In case of a mechanical system, F equals ma, that equals mdv by dt, which is md2x by dt2. Now, for an electrical system, E equals minus Ldi by dt, which equals minus Ld2q by dt2. Comparing these two equations, we see that L is analogous to mass m and L is a measure of resistance to change in current. In case of LC circuit, omega naught equals 1 by Lc, and for mass on a spring, omega naught equals k by m. So, 1 by c is analogous to k. The constant k, which is equal to F by x, tells us the external force required to produce the unit displacement, whereas 1 by c, that is equal to V by Q, tells us the potential difference required to store a unit charge. Now let's see the table giving the analogy between mechanical and electrical quantities. Click on the table button to see the table. Also click on the Know More button to know more about LC oscillations. The table below shows the analogies between mechanical and electrical quantities. LC oscillations is not realistic for two reasons. Note that the LC oscillations is not realistic for two reasons. First, every inductor has some resistance. The effect of this resistance is to introduce a damping effect on the charge and current in the circuit, and the oscillations finally die away. Second, even if the resistance were zero, the total energy of the system would not remain constant if it is radiated away from the system in the form of electromagnetic waves. In fact, radio and TV transmitters depend on this radiation. Let's take an example. Show that in the free oscillations of an LC circuit, the sum of energy stored in the capacitor and the inductor is constant in time. Solution. Let Q naught be the initial charge on a capacitor. Let the charged capacitor be connected to an inductor of inductance L. As we have studied, This LC circuit will sustain an oscillation with frequency as shown. At an instant t, charge Q on the capacitor and the current I are given by the equations shown respectively. Energy stored in the capacitor at time t is Q naught square by 2C into cos square omega t. Energy stored in the inductor at time t is half Li square, which is equal to Q naught square by 2C into sin square omega t. Sum of energies comes out to be equal to Q naught square by 2C. This sum is constant in time as Q naught and C both are time independent. Note that it is equal to the initial energy of the capacitor. Why it is so? Think.